It's 9 o'clock. Hi, welcome back. If you'll notice, I have my laptop out because a few people are actually for the week stranded. So through no fault of their own. So I've got to go ahead and record this. So before we begin, and I close these doors and I scream so that the computer can pick it up. There we go. Okay. So as you can see, I've got your exams graded here. Hopefully last week you got an email from me. I have a feeling quite a few of you struggled with this one, just kind of looking at the grades. The highest grade on the multiple choice component was a 60 out of 70, which translates to about an 85%. So again, I think this is a situation where I tried to make sure that the questions were kind of geared towards stuff, and I had the recorded review. And it looks like that may not have been enough. So if you checked your email, you will notice I said that we are going to be doing corrections for these ones again. Now, corrections only apply if you actually took the exam the first time. So we did actually have somebody who did not show up to take the test. Because they didn't take the test the first time, they have nothing to correct. Everybody else who took part in the multiple choice component can do corrections for the multiple choice component only. In general, I thought the take-home essays were pretty good. However, I did notice a couple of things that looked a little off to me. I noticed a couple of mentions in the answers of metabotropic glutamate receptors. So I saw a couple of responses that had mGlu6 mentioned and a couple of mentions of kinase receptors. Now, while I know what those are, I haven't actually taught about either of those things. So when I see mentions of receptors that I haven't really talked about in class, I get a little nervous. And it does kind of look like a few people may have used generative AI for their essay questions. Now, you shouldn't need to use AI or ChatGPT or anything like that to help you with these. Everything to answer the question has been talked about in the notes. They're in the book. You can even talk to me if you want. So this is just a warning. We have a third exam with a take-home essay. If I have reason to believe that AI has been used to generate your response, the next time I see it, it will be a 0. So please, if you're not sure how to answer the question, if you're not on the right track, please come and talk to me. I am happy to help you out. You do not need AI to help you answer these questions. Okay? So I thought that these were pretty good. So the corrections will only be for the multiple choice component. So if you have any questions, these will be for those of you who are here today. I noticed that not everybody is here, and for obvious reasons, some people will not be here all week. Again, some people are stranded and can't get back yet. But for those of you who are here today, those multiple choice corrections will be due on Monday of next week, so March 31st. Remember, the same rules apply. You have to tell me why you picked the answer that you did, what the correct answer is, and why it is correct, either using your notes, your book, or conversations with me as a source, okay? Any questions? No? All right. But here's the thing. Even with that in mind, I know that not everybody has the grade that they're hoping for right now. Obviously, the corrections and the zombie project that is coming up on the 21st will give you a little bit of a boost. But Most of you are passing, and for those of you who aren't, you're not that far off. If you do the corrections and if you keep coming and talking to me, you may not necessarily get an A, but I promise you that you will pass this class if you do the work and come and talk to me. Sounds good? Any questions before we begin? All right, so this week we are starting a brand new unit. We're talking about learning and memory. So this unit, I think, is probably going to be your favorite unit because we're going to be talking about learning and memory. We're going to be talking about stress and its effects on the brain and the body. And we're also going to finish up by talking about psychological disorders and the different types of treatments, including different types of medications that are used to treat those, as well as a little bit about how they work. So, I'm running two computers at the same time. This is going to be really interesting. So, really quick, turn to a classmate or jump a couple of seats over because I know we've got a little bit of spread here. Talk to a classmate for about a minute or two, and I want you to think and share with each other what comes to mind when you think about the word learning. So what sort of things pop into your head when you think about learning? So it is 9:06. We will go ahead and reconvene at 9:08. So talk with a classmate. What pops into your mind when you think about the word learning? All right, 9:08. Take a second to finish up any last minute thoughts that you had. Anybody want to share what came to mind when they thought about the word learning? Kenzie, Lilith, what came up for you? Okay, school. Raise your hand if your group talked about school at all for learning. What happened? Oh, that was weird. It went ahead like multiple slides. That was kind of bizarre. So school. Anybody else? What other things came to mind when you thought about the word learning? Yeah, Elizabeth.
Other aspects of life like driving, learning how to talk to people, I guess.
Okay.
Because that's not something that comes naturally to me.
Me neither. I get that. Anybody else? Yeah, Michaela.
We talked about retaining and like being able to recall.
Okay. So being able to reproduce things and learn things a little bit faster. So here, what if I told you that these are all different types of learning, but that learning is actually a lot more simple than just school? And what if I told you that learning is something that even some of the simplest creatures can actually demonstrate? So learning, we're going to basically say that learning is defined as a functional or a structural change in the nervous system. So learning, yes, school is a type of learning. repeating things to yourself and trying to remember really tricky things like neuroanatomy are absolutely a form of learning. But learning is all about adapting to experience. So here's a really goofy example of learning. And for those of you who are listening to this on recording, I am sorry that you won't be able to see this. So here's a really good example of learning. Ow. Let's try that again. That's learning. You learn and you change your behavior from experiences. You adapt to experience. So this creates functional and structural change in the nervous system. So researchers have actually found that animals like fruit flies can learn. Animals like lampreys can learn, and even cockroaches can show capabilities related to learning. So for example, if you put a cockroach in a chamber, one half of the chamber is dark and the other half of the chamber is light, where is the cockroach going to want to go? The dark, right? If it's in the light, there's a greater likelihood that somebody's going to try to stomp it. But if you apply a little bit of a foot shock to the cockroach, so if the dark portion of the chamber is wired with electricity, and when the cockroach stays in that chamber, it gets a little bit of a shock, the cockroach learns to avoid the darkness because the darkness is now associated with a foot shock. This was demonstrated by Minami and Dallenbach back in 1946. So learning is not just about school. Learning is also not just for human beings. So we're going to talk about a few different types of learning, and we are largely going to focus on human beings for this portion. So we can talk about perceptual learning. So learning different faces and being able to distinguish one person's face from another, learning different types of words, different types of sounds. We can do stimulus response, or what's sometimes known as associative learning. So things like operant conditioning, things like classical conditioning, or something very simple, just learning that here in the United States, when you're driving, a green light means go. We can also do what is called relational learning, and this is more complex, and this is based on different associations that we have in memory. So for example, I can show you a photograph, and that could trigger different types of sounds or words or different types of details related to that image. So learning can occur in a variety of different ways, and we're going to talk about each of these three types in greater detail. Now, the slides that I am showing you here match the slides that you have on MyCoddy. So if there are instances with a lot of writing, just know those are in full on your slides. So learning ultimately begins with our neurons. And one of the biggest proponents of this was Donald Hebb back in 1949. And so when we adapt to experience, when we change based through experience, we are basically changing our neurons. Now, what components of the neurons are actually changing when we learn something? Donald Hebb believed that it's the synapse that is changing. So when we say synaptic plasticity, when we use the word plastic, we're talking about something that is capable of change. So for example, my phone case is plastic. It's made out of a material that can be molded. So I could technically take this phone case, melt it, and basically mold it into anything that I wanted. It's plastic. It's capable of being changed. So learning happens because our synapses, the connections between our neurons, are capable of change. And it's the synapses changing that ultimately support neurons. Hebb believed that what was happening was sustained activation of what he called cell assemblies. You don't need to know what a cell assembly is. You just need to know that it's a group of neurons or a network of neurons. So if I repeatedly, through experience, activate that network over and over again, what ends up happening is that the synapse becomes stronger. It becomes a better sender of information and a better receiver of information. And what that means is that the synaptic strength increases and it becomes longer lasting over time. So here's what's really cool about Hebb's idea of learning. I don't have to create any new neurons for this change. The dendrites and the axon components in pre-existing neurons are what are changing. So the cell assemblies have to be plastic for this to work. This means they have to be capable of change. You don't actually have neurons that are made of plastic. Although you might have some microplastics in your brain, but that's not what we're talking about here. That's a different type of plastic. Does anybody have any questions? So you don't need to write this next part down, but here's the basic idea that Hebb wrote. So this is Hebb's component, and I'm going to sum this up in one very simple sentence. So this is in your slides. You don't have to write this down. But this is sometimes referred to as Hebb's rule or Hebb's law. When an axon of cell A is near enough to excite a cell B and repeatedly or persistently takes part in firing it, some growth process or metabolic change, he didn't actually know what the change was at the time, this was just an idea, some growth process or metabolic change takes place in one or both cells such that A's efficiency as one of the cells firing B is increased. So basically, everything that we talked about on the previous slide is summed up right here. So with repeated firing, if a cell repeatedly fires and activates another cell, that is going to create some kind of change that makes it more efficient. A simpler way to put this is that inputs that fire together wire together. So if the same two neurons are repeatedly involved in firing at each other for a certain experience, that's going to create a connection. And we'll talk about what is involved in that connection, but here's what's really critical. Note that in this quote and in this quote, I do not have to grow new neurons. I can make use of the neurons that already exist in this case. Does anybody need some more time here? Okay. So when we talk about what we know about learning, we're going to spend a lot of time with a very particular part of the brain known as the hippocampus. Now, raise your hand if you've heard of the hippocampus before. Now, if you've had me for cognitive psych, or if you took general psych either with myself or with Dr. Teets, you might have heard that if you damage the hippocampus, you will potentially develop some type of amnesia. And we are going to talk about that a little bit later on. Not today, unfortunately, but we will talk about it soon. But we're going to spend a lot of time focusing on this part of the brain right here. So if we take a coronal cut of the brain, so again, remember a coronal cut? It's like I'm putting a nice little crown on your head, and we cut straight down. Right here, where part of the brain curls inward, especially toward the midline, that's where our hippocampus is going to be. Part of the reason that the hippocampus has the name that it does is because from certain angles, it looks like a seahorse or a horse monster. So you can kind of see here, here's a seahorse. Here is a horse monster on Greek frescoes, but you can see that they have that very similar curvature to the hippocampus. If you want to be able to identify this on a neuroimaging scan, so here we have an MRI. Again, we have that coronal cut. You can see our two lateral horns of our ventricles. So you can see ventricle 1, ventricle 2. Here's your third ventricle and your fourth. And then right here, you can see these are where the hippocampi will be. So we have a right hippocampus and we have a left hippocampus. So this is how you would identify them. Now, the hippocampus is made up of a few different subparts. So I want to share these different parts with you, but do know I'm not going to test you on locations. Should you probably know that the Schaefer pathway is a part of the hippocampus? Yeah, but I'm not going to ask you where it's located. So, in particular, this is kind of a different view of the hippocampus. So we have a few different components here. In particular, we have areas like the dentate gyrus right here. We have areas like the entorhinal cortex, the subiculum right here, and then we have fields CA3 to CA1, and CA3 and CA1 are components of what is called the cornu ammonis. For those who are into ancient Egyptian mythology, that actually translates to Ammon's horn. Ammon is a god that kind of has the head of a ram. So this component right here kind of looks like a ram's horn. For the purposes of this slide, you just need to know a couple of major pathways here, and I am going to repeat these to you multiple times just to make sure that you've got it. We have one pathway here that is called the perforant pathway. The perforant pathway connects the entorhinal cortex to the dentate gyrus. So if you hear me talk about the perforant pathway, you just need to know that that's in the hippocampus. We have a Schaefer pathway as well, which connects areas CA3 to CA1. So if you hear me talk about the perforant pathway or the Schaefer pathway, you just need to know that this is a part of the hippocampus. So here kind of summed up are those major components. So the hippocampal region is made up of the dentate, which I showed you on the previous slide, CA1 through CA4, and an area called the subiculum. The hippocampus proper, so we have the hippocampal region and the hippocampus proper. The hippocampus proper is technically area CA3 to CA4. And as I said, CA stands for Cornu Amanus, or Ammon's horn. This is an ancient Egyptian ram god. And again, two major pathways that are going to show a lot of plasticity and a lot of capability of change in the hippocampus are the perforant pathway and then the Schaefer pathway. As I've mentioned, the perforant pathway connects the entorhinal cortex to the dentate, and the Schaefer pathway connects CA3 to CA1. And by the way, for those of you who might be wondering why I have a little laptop here, for some of our students who are currently stranded this week, I am recording these lectures this week, but that also means that you can watch these too. So if there's anything you need to go back and listen through, I will make this available on YouTube later this afternoon. Hopefully the mic works. No, I'm not kidding. 5 years ago, I had to record all of the back half of the Biopsych lectures when we were fully remote. And I got an email from a student that was like, your mic died halfway through one of the first lectures, and I had to get a new mic and record them all again. And I was just crying. I'm like, no. So if I do need to record this again, I will. Let me just put it to you that way. I'm prepared. Anybody need some more time here? So just in case you were kind of curious and you didn't know who Amun was, this is the ancient Egyptian ram god. You can see he has very nice ram's horns, and you can kind of see why that component of the hippocampus gets referred to as Ammon's horn or the Cornu Amanus. Now, you might be kind of curious as to how one can record from hippocampal slices, because a lot of how we've learned about how learning happens, basically what we are going to do is we're going to stimulate part of the hippocampus with a little bit of electricity, which makes sense, right? The main signal that neurons send when they're stimulated is electrical in nature. So we're going to stimulate one part of the hippocampus with electricity, and we're going to see how that changes in neurons that are downstream. So we're going to induce a change in some of the neurons and see how that changes the neurons that connect to that pathway. So what we have to do is we are going to basically take slices from the hippocampus. You can actually keep the cells alive in extracellular fluid or liquid that mimics an extracellular fluid. You can actually keep that slice alive for several days. And basically what you are going to do, so you can see in this image, we have the hippocampal slice. We have one electrode that is basically going to stimulate one part of the hippocampal pathway. It is going to stimulate that pathway by sending electrical pulses. So we're going to send a pulse of electricity repeatedly. And then from a section that is downstream, we are going to place a recording pipette. So for example, let's say that this is part of the Schaefer pathway. So this recording, this stimulating electrode is going to record in CA3, the beginning of that Schaefer pathway. And then the recording pipette is going to pick that up at the end of the Schaefer pathway in CA1. So if I induce a change in CA3, how will that change the neurons at the end of that pathway at CA1? So that's basically what we're going to do. We're going to stimulate one part of the hippocampal pathway, and then we're going to record from it. So one of the first people to do this was Turhe Lomo back in 1973. And in particular, he did a lot of his research from stimulating the perforant pathway in a rabbit and then recorded from the dentate. So again, just as a reminder, your perforant pathway begins in the entorhinal cortex and it terminates in the dentate. So we're going to stimulate axons here, and then we're going to record from the cells that make connections in the dentate. So again, how this is going to work is we're going to send an electrical pulse, and then we are going to see what happens in the neurons that connect downstream. And basically what Lomo found is that if you send one electrical pulse here, you get an EPSP and increased glutamate release in the dentate. So we stimulate an axon here, and the neurons that connect here in the dentate are going to have an excitatory postsynaptic potential. You're going to get a slight depolarization. The cell's going to become a little less negative, and you're going to get glutamate release. And glutamate is going to be really critical for a lot of learning. So that's just to a single pulse. So one electrical pulse here leads to a temporary change. But here's what's really cool. They delivered what is called a high frequency train of pulses. So they would deliver a bunch of electrical pulses in rapid fire succession. So instead of just going one pulse, boop, they would do multiple pulses, one right after the other, like that. And when you deliver multiple pulses in rapid fire succession, what they ended up finding was that for the dentate neurons that were downstream, they had a larger ESP and a longer lasting EPSP, not ESP. They had a lot. We are not doing telepathy here. Sorry, telepathy's not quite real. But they had a larger EPSP, and it was a longer lasting EPSP to a subsequent single pulse. So they would deliver a rapid fire train of pulses, a bunch of electrical pulses, and then they would deliver one more pulse to see what happened to these neurons in the dentate. And Lomo termed this long-term potentiation. Long-term potentiation, as we're going to talk about for the next couple of lectures, is the underlying cellular basis of all learning and memory. So long-term potentiation, basically a high-frequency pulse train to axons, will produce a larger and a longer lasting excitatory postsynaptic potential to a subsequent single pulse later on. So if you've ever had an instance, how many of you have been to a haunted house? Yeah, probably almost all of you. How many of you have had this happen where monsters are coming out at you and constantly startling you, right? You can kind of think about going to a haunted house and all of the monsters jumping out at you as that high frequency stimulation, right? Like they're scaring you, they're scaring you, they're scaring you. And then you get out of the haunted house, your friend tapping you on the shoulder is going to make you go, blah. That is the subsequent single pulse that you can kind of think of there. So that fear response is larger than it would normally be, and it lasts a little while longer because you were repeatedly scared and stimulated in the haunted house. Does that kind of make sense? That's kind of what LTP is like. You go into a haunted house, you get scared by a bunch of monsters, and then a single innocuous experience later on makes you produce a larger fear response than you normally would have. Kind of like that. So here's what those EPSPs kind of look like. So here is an example of what an EPSP would look like in those groups of neurons in the dentate. So here we deliver one single pulse. We get a nice EPSP that will eventually return to rest. Here's what's interesting. Let's say I introduce that high frequency train of pulses and then I deliver a single pulse after it. Long-term potentiation looks like these. So notice that this amplitude for this is much larger than it was prior. And you can see that that can last, that extra response can last for up to 96 hours, if not more. So you can see that there's a heightened response and that lasts for a very long time. Yeah, Lexi.
Why is there a bit of a dip at the 24-hour, but then it comes back up at 48?
I do not know. I do not know. What's kind of critical is that even at 24 hours, can you see that the amplitude is still a little bit bigger than even here? So here's that little dip. Notice that dip right here. It's even bigger. So it's different, but it's still higher than what we would see prior to that long-term potentiation. So this is a hard figure, and I've added these little boxes to kind of help you understand this a little bit better. So we've seen that this works in the perforant pathway. So just going back really quick, reminder that the perforant pathway is right here, entorhinal cortex to the dentate. We also can see this in the Schaefer pathway. So LTP, and again, a strong repetitive stimulus increases the response, not just in the dentate, but also we can find this in the Schaefer pathway as well. So LTP is found in the perforant pathway, so right here, and it's also found in the Schaefer pathway, which is right here, area CA3 to CA1. So LTP is largely found in the hippocampus. Now, the hippocampus is not the only place that we see this long-term potentiation. We also see this in areas like the amygdala. And we'll talk about how LTP in the amygdala can produce things like fear conditioning. But what you're looking at here is an instance of long-term potentiation in the Schaefer pathway. So here we have our stimulation. So we have that high frequency train of pulses in area CA3, and then we're going to go ahead and record from CA1. So we're specifically looking at this in the Schaefer pathway. Now, it's kind of hard to see in this figure, but for an interesting variable, they either did one high frequency train of pulses or they did 4 successive trains of pulses. And so here's what you're kind of seeing in this figure. So the y-axis here is the EPSP slope compared to baseline. So the higher that this is, if it's greater than 100%, that means that it's a bigger slope. There's a much larger EPSP. So the y-axis is the slope change relative to the control condition. Here, the control condition is the EPSP slope after a single pulse. So 100 is basically that baseline. And basically, they would either deliver 1 train of pulses or 4 trains of pulses, and they would basically get the slope of the EPSP by testing with a single pulse every minute after delivering those pulse trains. So here is early LTP, so here's the slope of the line with 1 pulse train. You can see that we have 300% larger than control. Here's after 2 pulses, here's after 3 pulses, Here's after 4 pulses. So you can see that with every single pulse, the slope of the EPSP relative to control gets larger and larger, and this stays sustained for over 3 hours. So notice that the slope continues to be quite high for subsequent single pulses, even 3 hours later. Almost 4 hours later. That's like 3.5 right there. So what is LTP and what causes it? So we are going to talk a little bit about glutamate now. So glutamate is really the biggest neurotransmitter that is going to be involved in learning and memory. Now, we've already talked about how important glutamate is for things like vision and hearing and our other senses. And some of you might be flashing back to bipolar cells and being like, please don't talk about bipolar cells ever again, Dr. Gilchrist. I won't. But glutamate is going to be really important for learning and memory as well. So glutamate is going to be critical. Now, there are metabotropic glutamate receptors. And as some of you may have noted in your essay, there is another type of glutamate receptor called the kainate receptor. I'm not going to talk about the kainate receptor here, but I want to talk about these 2 receptors in particular. These are going to be critical to the process. We have what are called AMPA receptors, and we have NMDA receptors. Now, occasionally somebody wants to know what AMPA receptor stands for. So I'm gonna try to read this to you for those of you who are curious. So the AMPA receptor stands for alpha amino 3 hydroxy 5 methyl 4 isoxazole propionic acid. Yeah, that's kind of a mouthful. Let's just call it AMPA. So AMPA receptors, they are basic sodium-potassium channels. So AMPA receptors are ionotropic. They are all about the flow of sodium-potassium channels, and they are going to be critical for creating EPSPs. EPSPs are going to be a really important part for the next stage of the process. So next, those EPSPs are going to be critical for NMDA receptors. So for those of you who are curious about what the NMDA receptor stands for, that is N-methyl D-aspartate. A little easier to read, but we're still going to call it NMDA. There we go. And these are calcium channels. So calcium is going to be a critical part of this process. Now, the reason that you need AMPA receptors to create an EPSP is that NMDA receptors have a little block of magnesium that prevents other ions from flowing inside. So it's going to prevent calcium from getting inside of the cell. So at rest, you have a magnesium block. You need the AMPA receptors to remove that magnesium block. So to open an NMDA receptor, 2 things need to happen. First of all, glutamate needs to bind to the receptor, and the cell needs to be slightly depolarized so that that magnesium block can be dislodged. So here's kind of what that looks like. So here's what's going on at rest. So calcium can't flow inside of the cell at rest because while glutamate is bound, that magnesium is there. And these ions cannot enter with that magnesium block. If the cell is slightly depolarized, that dislodges the magnesium block and allows calcium to flow inside. Calcium is going to be a very important part in this process. Calcium is basically going to exert a lot of cellular changes in this process. So, NMDA receptors are necessary for LTP. So sometimes we talk about what are called necessary conditions and we have what are called sufficient conditions. NMDA is not sufficient for LTP, but it is necessary. So in one experiment, researchers took a hippocampal slice and they applied a substance called AP5. AP5 basically is an NMDA receptor antagonist. What this means is that this substance prevents these channels from opening. NMDA is effectively blocked if AP5 is applied. And they did the standard LTP setup. They did a high frequency train of pulses. In this case, they did it in the perforant pathway of the hippocampus. And when this drug is applied that blocks the receptor, you don't get LTP. So when this NMDA receptor is blocked, you can't get LTP. So what this tells us is that NMDA receptors are necessary for LTP to happen. And calcium is a critical part of this process as well. So in another experiment, they had a hippocampal slice. They injected a substance called EGTA, which removes calcium and reduces calcium, and again, had this exact same setup, and the result was no LTP. So again, we need NMDA receptors for LTP to occur, and we also need calcium. So get some ice cream today at lunch, won't you? Dairy products, calcium fortification, it's good for you. Okay. So I'm going to go ahead and stop here, but next time we're going to talk about how we get that depolarization in the first place. So have a wonderful day. I will have this set to YouTube probably within the hour if you'd like to go back and watch it. I will go ahead and hand back your exams. Remember that corrections for the multiple choice only, for those of you who are here today, is due next Monday at class time. All right, have a great day, everybody. I will see you next time.